Bueno, hoy tenemos el placer de tener a un distinguidísimo científico entre nosotros, el profesor David MacMillan, y sí, creo que sí. Y la parte científica la va a presentar la profesora Carmen Nájera. Son viejos amigos y colegas del mismo campo, que no es el mío. Yo simplemente les agradezco que hayan venido en grandes números a esta academia, en la cual también pues tenemos a Nazario, que es la casa de Nazario, y también veo por aquí a Aguilar, está con el nombre a Manuel Aguilar, que también será su anfitrión en la charla que dará mañana en la Fundación Areces. Es decir, que si alguien quizás en esta charla le queda alguna cosa que quiere rematar, pues igual podría mañana también acudir a la Fundación Areces. No tengo en particular más que decirles, y que al final de la charla entregaremos al profesor MacMillan el diploma que acredita su membresía como correspondiente extranjero, y que posteriormente le pediremos que subamos al primer piso a firmar en el libro de honor, y durante ese periodo pueden estar ustedes todos presentes y no hay problema. De manera que con estas breves palabras, Carmen, presentas al eso, ¿no? Carmen will make the introduction, and afterwards the floor will be yours.
Okay. Good evening. Thank you very much for coming to this lecture, and it's a great honor for me to introduce Professor MacMillan. I have to say that thanks to the Areces Foundation, it was possible to invite David to come and to give a lecture not only here today but also tomorrow in the academy, in the Areces Foundation. In this case, the lecture would be at 7 o'clock. If somebody is interested to go to this lecture, you can tell to the students also that it's possible to come tomorrow. Well, for organic chemists, David is like an old friend because he has been in Spain so many times. Most of us know many things about his life, but anyway, I'm going to make an introduction for the young generation to let know that he studied chemistry at the University of Glasgow because he is a Scottish person. After that, he moved immediately to United States to Larry Oberman Lab to do the PhD during 5 years. That was in 91 till 96. And then he moved to Harvard to do the postdoc with A.B. Evans for 2 more years. And from this moment, he started his independent career. That was 98. That is important because if you know something about organocatalysis, you will realize what in a period of time he started to establish this new field and to put in the market the name of organocatalysis. That was in 2000 more or less. So in these 2 years as assistant professor at the University of California in Berkeley, he started his independent career, and then he moved to Caltech for almost 5 years, where he started as associate professor, and then as full professor. And in 2006, he moved to Princeton. And I have to say that he has been in the States for more than 30 years now. So you are more American than Scottish. He has received so many honors that we have here a long list, because when we presented him to become in this academy as academician, as foreign academician, But he sent to us a so long list of honors and students and lectures that would be impossible, and we prefer to listen to him. But just to mention that apart from the Nobel Prize in 2021, he has become last year, he was knighted in UK, and he's now Sir David MacMillan. So we should take care of that, because that is very important, especially in the UK. Yeah, but also if you have to fly and so on, if you put Sir in your passport, everything became easier. You know, you don't need to wait in the queue or things like that. You will realize that because you have just started to become Sir. As I told you, I prefer that he gave us to enjoy what he's going to speak about. For that, please, David, you can, the floor is yours. You can start with your lecture, with the name you know already, Development of Asymmetric Organocatalysis and Metallaphotoredox.
Okay, is the microphone working okay? Yeah, great. Number one, thank you, Carmen. That was a very generous, lovely introduction. I've known Carmen for a very long time, and we've always been good friends. And even today, we went for a coffee, and the first question she asked about is my daughter, and my wife, and my family. And I think that's just so fantastic, how such a warm person. To know you for many years has been my privilege. So for you to introduce me today in this event, as I become part of this group, is extremely, extremely, extremely special. So thank you for doing that. The second part is, she mentioned that I'm now in Britain known as Sir David. But I want to tell you, I never ask anyone to call me Sir David. No one in the world except one person, and that is my older brother. I tell my older brother, I insist he call me Sir David all the time. Okay, it's great to be here. I apologize for those of you who are not chemists. For those of you who are not chemists, this is going to be a very boring lecture. For those of you who are chemists, this may also be a very boring lecture, but I guarantee for the non-chemists. But tomorrow at the RSS Foundation, I will give a much more general talk for general public, for non-chemists, and I will also tell some stories about what it's like to win the Nobel Prize. Hopefully funny stories, although you can determine if you decide to come. But it is a very unique and unusual experience, and so I like to tell some hopefully interesting stories, and if you're interested, please come tomorrow. Okay, so I'm not really going to talk about organocatalysis today. This was an area my group was involved with for 10 years. But what it did for my group is it allowed us to move into another area, an area called photoredox catalysis, which really, organocatalysis for us really was the bridge that led us to photoredox. Now, photoredox in itself maybe is even bigger field now than organocatalysis. So, for us, it's been a very exciting field to be part of for a reasonably long period of time. Okay. So what is photoredox catalysis? Well, for the physicists and for those of you who don't know this area, it's really taking the ideas that have been learned in physics and chemistry about trying to store solar energy and use it to power the planet, but to take those ideas and to use them for organic chemistry, hopefully to make medicines as well as flavors and fragrances, agrochemicals. And this has led to this world called photoredox catalysis, where using light, visible light, blue light, as well as some other colors, we can now do lots of organic chemistry that previously was not possible. Okay, so this area, photoredox catalysis, over the last 15 years has become quite large. It's become quite a large area. And after winning the Nobel Prize, even though it was for organocatalysis, people asked me, why did photoredox become such a well-known area? Which is an interesting question, and it made me sit back and think about this. Why did it become reasonably well known within organic chemistry? And I think there's a couple of very important reasons. The first one is it allows you to take these chemical feedstocks Those are molecules which are available all over the world, they're abundant, but normally we think of them as not being reactive. And by channeling, using these photocatalysts and using visible light, we can then take these very stable molecules which are available in diverse structural formats and now make them into very reactive, very high energy species. And using that, we can now use those species to invent completely new chemical reactions. These new chemical reactions, because of the diversity of structure and the commercial availability of all these starting materials, has led to the fact that predominantly people who make medicine, the pharmaceutical companies, have adopted photoredox catalysis extensively. And for those of you who don't know this, the biggest group of chemists on the world are medicinal chemists. There's roughly about 500,000 medicinal chemists on the planet. And they use different chemical reactions from each other every single day. And therefore it becomes important that they have ones which allow them to rapidly make drug-like molecules. Okay, within photoredox, that's photoredox, but within photoredox, there's a subfield, and that is metallaphotoredox. And that is the idea of being able to take photocatalysis, or the ideas behind photocatalysis, and merge it with metal catalysis, or many traditional ways of being able to perform cross-coupling reactions. Now, by merging these two areas, this has become a subfield, and we started working in this area about probably almost 10 years ago, actually 10 years ago now. And we had a very simple idea. The simple idea is shown here, and the idea is that we would be able to take these aromatic bromides and these nickel 1 or nickel 0 species, and in combination, we know that those will do oxidative addition to generate these nickel 2 aryl species. But what was also known was the idea that you could actually take radicals and that radicals would trap nickel 2. And if these radicals can trap nickel 2, that means they can then do reductive elimination to generate these types of products. So why is that interesting? Well, that's interesting because in the previous slide, I just told you that photoredox is really good at generating radicals from feedstock chemicals. So as such, potentially, you could start to do cross-coupling chemistry with feedstock chemicals. Our first interest in doing this was to use abundant biomass, such as amino acid. This is proline. And the idea here is that using light and using these catalysts, we could decarboxylate these. And by decarboxylating them now, you could effectively start to think about being able to use this abundant biomass as actually cross-coupling partners for being able to generate pharmaceuticals. Now, I'll point out we were not the only people doing this. We actually, our first paper in this area was published exactly the same time as Gary Molander, who at Penn really did a beautiful piece of chemistry using trifluoroborate salts to effectively do exactly the same thing. Now, our first paper on this was published back in 2014, the whole idea that you can use abundant biomass to do cross-coupling. And I'll be very honest with you, we took this idea and we exploited it in many different directions. So we used this whole concept to publish many different papers. These are just some of the ones which are shown here. Now, I've been very lucky over the last 20 years in that I've been asked by a lot of different pharmaceutical companies. I consult for 10 major pharmaceutical companies on making medicines. And I get to travel to all these pharmaceutical companies over the last 20 years, and I get to see what they're doing and what chemical reactions they are using. And I would ask them, which ones do you actually use of photoredox? And they would say, it's really interesting. We would use all of these ones showing in this right-hand side. These are the ones that we'd use basically every day. However, the very first one that we developed, the one on the left-hand side, effectively shown here, they said they didn't use it very much, which was very disappointing. This is the first one you develop, and they tell you that no one's really using it. And we asked them why. And they said, well, it's not general enough. It only works about 20% of the time, but 80% of the time doesn't work. So we don't use it because we're worried that it's just not going to work 80% of the time. Now, you may look at that and say, well, that's okay. Why would you worry about this? Because we know that the one on the right-hand side is working very well. Why would you care about making the left-hand one work? Well, let me explain to you why we felt it was really important to think about the generality of this reaction. If I show you what are the availability in the world of these molecules in terms of them being either an iodide, a bromide, or a chloride, they're reasonably commercially available. And in terms of which ones people actually use, the bromide is the ones that people most use. But if you compare that against carboxylic acids, which are shown here, you can see there's much, much more of these that are available in the world, and yet people don't really use it to do these kind of chemistry. For that reason, we thought we should try and make this reaction general using carboxylic acids. So that became our focus. Now, I would argue that organic chemists, we care a lot about invention. We care a lot about the impact of a reaction. We care a lot about selectivity. We care about yield. But one thing we don't spend an enormous amount of time thinking about is generality, even though that might be the most important point of any chemical reaction. Okay, so if you think about how do we normally get to generality, how does generality happen for a chemical reaction? Well, it's normally, as shown here, is that you will have a reaction, you'll study it, you'll have a mechanistic insight, that will move over into reaction development, and eventually that will lead to an improved reaction. That's normally how this works. But this is an iterative process, because once we've accomplished this part, we then go right back to the beginning, start all over again, and we keep going round and round and round in this cycle. Now, several very important reactions and are shown in this slide. These are some of the most important chemical reactions in the world. Olefin metathesis, which did receive a Nobel Prize. CN cross-coupling on the left-hand side, which I would argue probably will receive a Nobel Prize. And CH alkylation, again, I think will probably receive a Nobel Prize. These are all transformations which are important because they're so general. Now, if I focus in on one of them, this is CN cross-coupling, developed by Buchwald and Hartwig. You can see that this is the evolution of the catalysts that were required for this to become general. And this was really beautiful work. But at the same time, you have to concede that this actually takes a reasonably long period of time for this to happen. This took decades for this reaction to become general. And one way you can demonstrate this, and I have permission to show this, is if I think about Steve Buchwald. So this is Steve when he first started developing the reaction on the left-hand side, and this is what he looks like now. I actually think he looks fantastic now. But the point being is, I don't have 30 years to think about making a reaction general. That's too long of a time frame. So what are we going to do? How do we accelerate our approach to reaction generality? Well, we decided we wanted to do this. We had to stop thinking like chemists and actually start to think like biologists. How would a biologist think about this problem? Well, what a biologist would do is they'd think about phenotypic approach or phenotypic evaluation. So the idea here is, imagine we can do a high throughput additive approach to identify a hit to ultimately lead to a general reaction. And once we actually have a general reaction, then understand why it works. This is often how biological mechanisms happen. You get a phenotypic outcome, and then you go back to try and understand where that phenotypic outcome came from. So we thought, could we do the whole same thing for chemistry? All right, now to do this, we actually had to get involved with a collaboration with some folks at Merck. This is Spencer Dreyer and Shane Kriska, who were from Merck, along with Jacob, and Nico Prieto-Comer. Nico is actually Spanish. He did his undergraduate degree here in Madrid, and he came over to do a PhD in my lab, and he's been absolutely fantastic. He's someone to look out for the future. But with these four people in hand, we started to think about, could we actually use high throughput evaluation and using these technologies that Merck had to try and achieve this generality? So how do you do that? How do you solve generality? Now, not thinking like a chemist, you realize that you can't look at one individual reaction at a time. It doesn't make sense. That doesn't tell you if it's going to be general. What you have to do is simultaneously evaluate large classes of molecules all at the same moment. So to do that, we had to look at all of the potentially different types of substrates and evaluate them all at the same moment. That became pretty critical. The second thing is we had to do these in a high throughput fashion. Merck actually had this fantastic nanoscale platform, which allows you to perform more than 10,000 reactions and analyze them on any given day, which is a very large number of chemical processes. Okay, so we did that. We performed these high throughput evaluation, and in this case, we actually looked at 721 additives. When we looked at those, this is the normal. This dotted line here is your sort of the typical efficiency in which you would normally see. And you can see in this case, most things at about the typical efficiency level we achieved already. A lot of different additives actually made this chemical reaction not so good, it was detrimental. But very interestingly, we started to notice there were certain ones which actually were given almost a 5-fold improvement in efficiency across the board. When we actually looked at those chemical structures, I would say even to the non-chemists in the audience, if you look at this, you can see that these all look similar to each other as chemicals. They're all from the same structural class of what's called 5-membered imides. With this information in hand, we then performed 3,000 chemical reactions just to study the imides themselves. And when we did that, what we found out was really pretty fascinating. First of all, you have to have this 5-membered imide. It can have a ring associated with it, either aromatic or non-aromatic, but this nitrogen has to be unsubstituted. It has to be an NH. And if you know this world, or this field, you probably think it's quite ironic, but the best additive that we found was actually a thing called phthalimide, which is really great because phthalimide is incredibly inexpensive, very cheap molecule. Okay, now we believe at this stage that we've found a way to make this reaction general. But how do you convince the world that it's general? How do you do that? That's not normally how we would put a manuscript together, for example. Well, the way we had to do it, we had a couple of different approaches. One is that Merck actually have this library of compounds, and every time someone publishes a new chemical reaction, they test it with this library of compounds because they know they're often very difficult, if not impossible, to be used in most cross-coupling reactions. And after they test it, they give it a score. There's 18 compounds, it's basically a score out of 18. I'm just showing you 8 of them. So we took those 18 compounds and we tested them. This is, first of all, without the phthalimide, without the additive. And you can see here, most of these reactions are terrible, basically where we started from. One of them is 50%, but most of them are pretty terrible. However, if you now add phthalimides simply to these reactions, they all now bump up to about 50%. And if you're a medicinal chemist, if you're involved in drug discovery, these yields are great. These are yields that will allow the program to go forward. So you're now taking things that weren't working and you're making them into being useful simply by just adding phthalimide to it. Now, that's one way of sort of approaching the problem. The second way we wanted to do it was to actually just show the delta in the efficiency across all these different classes. So this is just the delta average-wise for all these different molecular classes. You can see for most of these, you're seeing a delta increase. The tertiary, the second from the right in the middle row, we'll come back to and talk about in a few moments. But for most carboxylic acids, this is now working. In fact, if you look at the aromatic bromides, which would also be involved here, you effectively see the same thing. So this was a nice way of being able to demonstrate that this really has become a general chemical reaction. Okay, so that's all well and good, but you could make an argument this is still phenotypic. We've had an outcome, we've found the way to make it general, but we don't know why. We don't understand why it's made it general. So the next question became, can we achieve mechanistic insight? Can we look at the fundamentals to understand what is going on? So this was really fascinating to me at this moment, because what I thought was going to happen is we'd study this reaction and we'd find basically an on-off switch. The adding phthalimide would switch on in some way and wouldn't switch on in another way, and that would be the answer to everything. And that was absolutely not the case. What we actually found was that phthalimide actually rescues this chemical reaction in 6 completely different ways. So I'm actually going to show you just 5 of these. It's late on a Wednesday evening. I'm not going to go through all of these. But there's really 6 different ways in which it actually rescues this reaction. I'll show you 2 of them really quickly because I think this is really, really wonderful. The first one is, I told you at the very beginning, when you take an aromatic bromide of nickel, it does this thing called oxidative addition. And when you do oxidative addition in the presence of a carboxylate, the carboxylate binds to one of these coordination sites on nickel. However, when you do it in the presence of phthalimide, it's replaced by phthalimide. That sort of makes sense. But the key part here is this adduct with the carboxylate here is very unstable. And it basically falls apart, it decomposes, and it places a proton right on this aromatic ring. When you do this with phthalimide, that doesn't happen. It's completely stable, it's a rock. And in fact, you can get a crystal structure of it, and taking even that crystal structure, adding a radical, it will undergo addition followed by reductive elimination. So that's pretty interesting. It's effectively allowing the formation of an oxidative addition adduct, which basically just hangs out and waits for a radical to be generated so that it can trap it. That was number 1. I'll just show you a second one. I think this is pretty neat. This is the normal reaction we'd perform without phthalimide. And you can see here, the reaction begins and almost immediately stalls. It starts off and then quickly flatlines. It's not going anywhere. And the reason, when you dig into this, is because these nickel-1 complexes actually form these bridge dimers. These bridges are very stable. They're so stable, they won't do any more chemistry, they won't do any more oxidative addition. You can even throw in aromatic iodides, nothing happens. Just completely static. What's interesting, however, if you take that reaction that had been stalled right down here and simply add in phthalimide and it re-triggers it, it kicks back in and off it goes again. So what is happening? Well, what is happening is the phthalimide is actually breaking up this bridge dimer and pulling them back to becoming monomers, which allows the chemistry to just keep on going. Now, the thing I found fascinating about having 6 different components is if you imagine trying to do this the way a chemist would normally try and evaluate this reaction, you'd have to solve all of those 6 mechanistic problems separately and then try and come up with a molecule that would do all of them at once, and that almost seems completely impossible. But using the phenotypic approach, where you're just finding out what actually allows all of them to be solved simultaneously, that takes you to the answer and allows you to get to these mechanistic details. So the key thing in all of this, and the thing I'm most excited about, is if you go back to this reaction that was previously not general, this is now up to about 85% completion success, and now is being heavily adopted by the pharmaceutical industry, which was exactly one of the reasons why we were excited to do this in the first place. This was some chemistry that was published back last year. All right, so you look at that and you start to think, well, that's great, but you start to think, well, what other pieces of chemistry would you hope to develop that would also be general, that would work so broadly? And to sort of answer that question, I'm going to take you back to this kind of bar graph, and just to remind you, on the left-hand side is molecules or feedstock chemicals that are available, readily available on Earth, that you can buy directly. And on the right-hand side is their actual application. You can see there's this mismatch between acids, which is now growing, and bromides. But you can see there's a space at the bottom here, and the space has been left that way because there's actually another functional group which is far more abundant on Earth, and that is alcohols. Alcohols are literally available in incredible structural diversity. But in terms of using them for cross-coupling reactions to form carbon-carbon bonds, there's basically no general strategies to do that. So with that in mind, we thought that was a great reason to start to think about this problem. And if you're wondering why you would want to do this, I'll give you one example. Imagine you could take Taxol. Taxol is one of the most successful breast cancer treatments on the planet. And man, you know that Taxol has this alcohol, which is located right there. But imagine you could just simply devise a reaction where you could stitch in aromatic rings directly in one step, and think about how potentially valuable that could actually be. All right, so how are we going to do this? How are we going to solve this for alcohols? So the premise became, well, what if we could design some type of reagent that when you treat it with an alcohol will, within 5 minutes, associate with the alcohol, and then when you expose it to visible light and a photocatalyst will undergo formation of a radical. Remember, we need those radicals to interface with nickel to do cross-coupling chemistry. Now, we thought about this for a long time, didn't really go anywhere, but then this really wonderful postdoc in my group, Zhe Dong, Zhe is now a professor back in Shenzhen in China at SUSTech and doing some really beautiful things. But Zhe came up with this really fantastic idea, and I'll give a little bit of the story away by telling you that this NHC complex is now made on a very large scale. It's sold by most chemical vendors now. It's now become one of the most popular reactions in the pharmaceutical industry. But the original idea that Zhe had was, if you take an alcohol and an NHC, it's known that it will interact with that alcohol very, very quickly. Now, if you expose that to photoredox conditions, this should form a radical here. And if you know organic chemistry, you know that will very rapidly do beta scission to give you this very stable byproduct. And this radical, which should now interface with nickel, and then go off to give you this cross-coupled product. That was the hope anyway. Okay, now, as it turns out, this reaction works extraordinarily well. I'm not going to go through all the scope, because it feels a little bit like reading the phone book at some point, just given lots of scope. So what I thought I'd do is just give you a very quick overview. But even using things like trifluoroethanol, because we know that forming a radical here is very, very high energy. But again, this works just fine, and even taking 2 diols. So we can now stitch in aromatics directly into these places. Bicyclics, strain bicyclic, bridge bicyclics, you can stitch in these aromatics, even in the presence of functionality we think of as being pretty potentially accessible to metal catalysis. Remember I told you tertiaries were difficult in that previous slide. We can now, in fact, stitch in tertiaries. And even taking carbohydrates, sugars at the anomeric position, or even on the backbone, we can start to stitch these things in. One part of this, which was completely serendipitous, it was completely lucky, was we started to look at using 1,2 diols. When you get a 1,2 diol, you imagine, well, both alcohols are just going to react to give you the 2 aromatic installation. But what happened, which was kind of fascinating, when we ran this reaction, it only did it once. It didn't do it twice. We now understand why. If you're interested, we can talk about it later. But the beautiful thing was it only installs 1 aromatic. The reason that's valuable is you can then take the remaining alcohol, which is left behind, and stitch in another aromatic. So you're now making drug molecules enantiomer and in 2 steps from these very simple building blocks that obviously anyone can purchase. And I opened this up by saying, wouldn't it be great if you could take Taxol or simvastatin? You can actually take Taxol. This is 25% yield. It's not the world's greatest yield. But the fact that you can take a molecule of that level of complexity and now stitch in an aromatic directly at that position, we think, obviously, again, lots of underlying utility that's going to be associated with that. Now, as any good academic knows, whenever you hit a theme or a part of success in something, you start to think about different ways and different directions you can take that in. And we've certainly started to think about different ways in which we can take these alcohols and now start to utilize those to do lots of different types of chemistry. This is no longer just merging it with nickel, we're now merging this with lots of other metals. For example, we can take alcohols, make them into CF3s. Many of you will know CF3s are a unit or subgroup that's heavily now used in the pharmaceutical industry because of the metabolic stability. You can do Giza additions directly into these positions. You can do alkylations where you deoxygenate with a sp3 bromide to do carbon-carbon bond formation. And you can now even do sulfonylation. You can convert alcohols over to sulfonamines. And all of these things are simply by using this NHC in combination of alcohols to allow the formation of that radical system. Okay, for the second part of this talk, and this will be probably about another 5 to 10 minutes worth, what I thought I would also introduce you to was this question of benzene bioisosteres. For those of you who don't know what a benzene bioisostere is, it's basically on the left-hand side. When you look at pharmaceuticals or medicines, you often see these benzene rings or these aromatic rings such as the one shown here. But often these molecules will fail in the clinic. And they'll fail in the clinic for numerous reasons, but one of them is metabolism and the other one is solubility. Because of the nature of the aromatic rings and also because cytochrome P450s, which are in your body and your liver, can very readily oxidize them, which allows your body to clear the medicine before it can actually have any value. What people have started to do is to invent these molecules such as these weird looking BCPs, or even starting to think about using cubanes to replace those aromatic rings, with the idea here being that it is much more difficult for these things to undergo metabolism because the CH bond strengths are just way too strong. And they're also far more soluble because they don't basically undergo any kind of pi stacking interaction that allows crystal formation to actually happen. So this is work that we actually did in collaboration with Merck over in the US. The people involved from my group were Mario, Olivia, James, Johannes, and Florian, and Johnny, Charles, and Jashin are all from the Merck Cambridge site. The point of all of this was, while basically these types of molecules, these BCPs, have been reasonably well studied over the last 5 years, there's been almost nothing that has been performed with cubane. Cubane, as the name suggests, is a molecule which is basically a cubic form of carbon. So why are people interested in cubane? Well, people have been interested in cubane for a long time. One of the reasons actually is that people thought you can maybe use it as a fuel because it's so much strain energy actually boxed up in the cubic form. But they've also been really interested because back in the 60s and the 70s, Phil Eaton had a hypothesis that cubane is the perfect benzene isoster. And the reason why that is if you think about the substituents or the vectors that can come from benzene rings, you can imagine almost exactly the same vectors that can be positioned around a cubane ring system. But the key difference here is the CH bonds in cubane are so much stronger that they're not going to undergo oxidation the way that benzene rings can. And in fact, people have started to think about ways of introducing cubanes into drug-like molecules. All right, so I'll show you this slide, which I think is just absolutely fascinating. So this hypothesis has been around in the chemistry community for 50 years, basically. And every medicinal chemist and every pharmaceutical chemist you talk to knows about it. They've all discussed it. But if you actually go and use the metric of patents, to see how many times people have actually used it. It's basically uncharted territory. Well, there's more than 500 patents on the BCP on the left-hand side. Cubanes, with this vector 1-4 relationship, less than 100. The 1-2 and the 1-3, less than 5 patents in the whole world. That's incredible. So why is that? We've got this hypothesis, everyone knows about it, but there's no patents. Well, what is going on here? Why is it underdeveloped as a benzene isoster? Well, it's very simple. While cubanes are tolerated by your body, cubanes are not tolerated by modern synthetic chemistry. What do I mean by that? Well, if you take most modern synthetic chemical reactions that involve metals, such as the one showed here, if you try to use them to actually couple on other molecules, it doesn't work. It doesn't work because the metals will actually insert into these strained carbon-carbon bonds, and in doing so will actually rearrange these molecules to the point that they're not cubanes anymore, and certainly not useful anymore in this context. So in this case, we started to think about how do we solve this problem? So the problem is that we need to somehow get away from this issue where these metals will do oxidative addition into these carbon-carbon bonds, but we also need to speed up the step where this part happens, where it couples on the other molecule. How do you do both of those at the same time? So our solution to this was copper catalysis. Why copper catalysis? Well, it's well known, if you think about where copper is in the periodic table and how electronegative it is, it's absolutely terrible at oxidative addition. It doesn't have that electron-rich component which will allow it to undergo addition into those strained carbon-carbon bonds. But because it is so electronegative, it's fantastic at doing the second step, reductive elimination. So we actually took advantage of this a few years ago when we were trying to figure out how to do trifluoromethylation of an aromatic bromide, and by not doing oxidative addition, if we could actually form a radical on the aromatic that's shown here, it's well known that those radicals will actually trap copper at almost diffusion rate control, and then subsequently is set up for reductive elimination. You can see in this case it's installing a CF3 where that radical used to be. So not surprisingly, we said, well, maybe we could do exactly the same thing with cubanes. What if you could indeed generate the radical on the cubane? Can it trap copper at diffusion rate, and then can it do reductive elimination to solve this problem? Okay, so we set out to test this, and it was really satisfying. It worked really nicely. First of all, arylation, amination, alkylation, even trifluoromethylation, and we've shown more than 30 examples of each of these now, and demonstrating there really can achieve modularity with the synthesis of these cubanes for drug-like synthesis. So that's all well and good. But then the second part comes up to be, we've obviously solved this for these 1-4 vectors positioned here, but what about these 1-2 and these 1-3? What is the problem there? Well, the problem is to get to the 1-2 or the 1-3, it actually involves 11 chemical steps from this commercial material, or 9 chemical steps from the same material to make the 1-3, and there's no medicinal chemist on the planet who's going to go through 11 chemical steps to make something just to test it for one attempt. That's just not going to happen. So again, we started to think, can we use photochemistry to solve this problem? And indeed, we've now, we think, done that. We've used dihydropyrazine to make the 1-3 cubane, and in 4 steps, we can now, from the 1-4 cubane, we can make the 1-2. So those have now been commercialized based on the synthesis by Enamine, who are basically over in Ukraine and some of it in Poland, and they've now commercialized that for the whole world. But the critical part is, can you actually use it to actually do these modular attachments? And now for amination, arylation, alkylation, you can do exactly that. So this is a paper, it just came out, I think, it just basically came out recently. There's a number of companies that have now been founded on this paper, with the whole idea now of, can you actually take cubanes and replace all these aromatics in drugs? And by doing so, number one, can you get better drugs? But number two, there's all these other aspects of this that could be really exciting, that could be associated with this. All right, in the last 10 minutes or so, I'll finish off with a new piece of chemistry that we're very excited about. And I would say that, with no exaggeration, I think this is going to be probably the foundation of what my group is really focused on for the next 3 to 4 years. And this is what we would describe as, it's not really a new mechanism, but it is a new mechanism for carbon-carbon bond formation, which is called SH2. So the basis of this is really pretty simple. The basis is, if you look at all these papers that have been published in medicinal chemistry, what those papers are now saying is, as you get closer and closer to the market, as you get closer and closer to clinical trials, you actually have more and more what's called sp3 carbon content. sp3, meaning you need more of these types of bonds and less of these aromatic circumstances. And the more of these sp3 you have, the more likely it is you're going to achieve a useful drug. And every time you talk to people in the pharmaceutical industry, they keep asking us, can you get more and more sp3 carbon-based reactions instead of aromatic ones? So okay, so I was sitting at my desk one day and trying to come up with some interesting idea and not going anywhere. And I started to think about this sort of not particularly well thought through concept. As I showed you at the very beginning of my talk, 4-redox is fantastic at generating radicals from a whole host of different feedstocks. So the question became, imagine you can take two completely different molecules and you can sort of simultaneously generate radicals from both of them, such as shown here. Could you in fact get them to undergo coupling with each other? Because it's known that radical-radical combination is effectively barrierless. So there should be absolutely no reason those should not couple to form that type of bond. For the chemists in the audience, you immediately see the problem. There's a huge problem, and that is, well, yeah, but it can do that, but it can do lots of other things too. These radicals can react with themselves, they can react with solvent, they can do all these different things. This is going to be just a disaster. However, being an optimist, I asked one of my postdocs to go into the lab and try it, and he came back and he informed me, yes, it was a disaster. It was completely a terrible idea. But this is why it's great to have fantastic people in your lab, because he said, well, you know, based on your concept, have you ever thought about cobalamin? And I was like, yeah, I haven't really thought about cobalamin much. What are you asking me? And he said, well, cobalamin does this thing called SH2 chemistry, which is kind of along the same kind of lines. Now, I'll be honest with you, I didn't really know what SH2 chemistry was 4 years ago, which is something embarrassing to admit. But for the chemists, what an SH2 mechanism really is completely identical to an SN2 mechanism. It's just where a radical undergoes an addition, and the leaving group is a radical. And metals, through the change in their oxidation state, are fantastic radical leaving groups. That's how, in nature uses radicals to form carbon-carbon bonds using SH2. And I love this statement. It was by Michael Johnson. It was in 1983, but it said, seldom postulated, rarely discussed, frequently discarded as improbable, but potentially of immense interest in synthetic organic chemistry. So we started to think, could we use this SH2 chemistry to effectively take these sp3 carbons and start stitching them together? Okay, so why would this work? Why would this work? Well, basically the idea here is, imagine we take some catalyst and we can generate a primary and a tertiary radical at exactly the same moment. Now, we believe this primary radical should immediately bond to this metal center, and then the tertiary radical should be able to do SH2 and give you a cross-selective product. Okay, so why would this, for example, only do this reaction, as opposed to why wouldn't the primary simply react with the same molecule? Well, as it happens, these primaries are not nucleophilic. They're much less nucleophilic in tertiary, which means the rate of this reaction should be so much slower. So then the question becomes, well, why wouldn't the tertiary simply bind and then react with itself? Well, first of all, we believe that it's highly unlikely this would form. That's such a strained bond, it actually has a negative bond strength. And even then, for the radical to undergo an addition to this tetrahedral carbon seems so unlikely, that doesn't seem feasible. So the only thing that's left is cross-selective. So we've now termed this radical sorting, because the mechanism will sort out the radicals to only allow them to react with each other and not go near themselves. That's the whole premise behind it. So the question becomes, does it actually work? So this was a fantastic collaboration with an amazing group here in Spain. This was the Janssen folks down in Toledo, as you know, very close to here. This was with Jesus Alcazar, who worked with us on this. And this was just an amazing collaboration. I'll show you another collaboration we have with them in a couple of moments. But the idea here was, could we actually, with the postdoc I told you who came up with this idea was Weilu, that's him there. He now works for Janssen. This is Marissa, who's now doing a postdoc at MIT. This is Colin, who's a postdoc in my group, who's now going to market this year and is going to be doing extraordinarily well. But the point here is, can you take these two molecules and can you simultaneously generate radicals from both of them? And can they sort themselves out through this catalyst to only do selective cross-coupling? So we attempted this, and I'll not go on to all the scope again, but here are just basically the typical reaction partners that we use here. And what's fascinating is you can in fact form these two radicals that do connect with very good efficiency, and it's very highly cross-selective. It really does do radical sorting. It sorts itself out to form these types of products and generate, and this was a paper that we published back in 2021. But immediately upon publishing that paper, you start to think this concept should be exportable to lots of different chemical reactions and potentially lots of different metals. Can you use radical sorting to do lots of different types of chemistry? That's the first thing you think about. Now, if you actually go back to the literature and look to see what metals have actually been used to do SH2, there's only 3 metals in the literature that have been documented as doing SH2. We've now found 10 different transition metals in the periodic table that do SH2. And the reason that's so important is that starts to give you all these different levers or nuances in which you can start to use those bond strengths in completely different ways to do completely different chemical reactions, which is obviously something we're pretty excited about. But let me show you just a couple of examples. So here's one. This is one we developed. This is now using nickel as an SH2 catalyst. This is Lorenzo and Artem. And the concept here is, imagine you can take 2 carboxylic acids. For those of you who are not chemists, this is vinegar. This is acetic acid. And this is another carboxylic acid. And the only difference between these, they're both carboxylic acids, is that one's a secondary carbon, and that one's a primary carbon. But what we're going to ask it is to perform the reaction, and then it's going to do radical sorting so that this methyl will only connect there when that decarboxylates to generate that product as shown over here. Now, the reason why we thought this would work is we use these iodoso-mesylylene systems, which forms these dicarboxylates. It doesn't matter that these are a mixture, because when you treat them with light and a photocatalyst, you should absolutely undergo this IO bond photolysis and effectively create both of those radicals at the same time as each other, hopefully without allowing this to undergo radical sorting. Okay, so when you test this, and just keep your eye on the pink spot here, what we're going to try and do is take vinegar and use the methyl of vinegar and stitch it into where these pink spots are. And when you do that, it works really well. It beautifully sort of does that with very good levels of efficiency. And indeed, you can start to go beyond vinegar. You can do all these other primaries. And as long as you've got a primary with a secondary or a primary with a tertiary, this chemistry works absolutely fine. It starts to connect with very good levels of cross-selectivity. This is for the real synthetic aficionados in the audience. This points out you can do this on a drug molecule, you can do it on a very complex natural product, or you can do it on a malaria drug, which has very sensitive functionality associated with it. And you can see in all of these cases now, you're being able to connect these things with high levels of efficiency to stitch on these alkyl groups. I'll show you one other chemical reaction, and I'll go back to the same way of conceptualizing it. Remember, I'd shown you before all the different types of functional groups in terms of their availability on Earth. I've sort of taken that bar graph and flipped it around. It's now on the bottom line. And you can see the 2 most well-known or available functional groups beyond CH has alcohols, as I mentioned before, and carboxylic acids. Now, we all know if you were to try and think about taking an alcohol and an acid and putting them together, that's one of the first reactions you ever learn in organic chemistry. That's where you make soap. That's where you make esters, such as the one shown here. But this is traditional cross-coupling. Imagine we could deoxygenate and decarboxylate so that these were actually 2 radicals and stitch those together. Wouldn't that, we would argue, could be useful? So this is the work of Holt Sakai. He's now, he's a fantastic graduate student. He's now off doing postdoctoral studies with David Liu at Harvard. And he published this paper with more than 70 examples, but I'm only going to point out that the way that we actually perform this is we actually take 2 reagents and 2 catalysts, put it in a vessel, put it all together, and simply shine light on it and hope that the radicals will form and then sort themselves out to give you the desired products. And in fact, these are just some examples that I'll show you. But again, we're using secondary with primary or tertiary with primary. And again, nicely will form these radicals and stitch themselves together with good levels of efficiency. All right, I'm basically done. I'll show you one other quick, not even one study, I'll show you one example to make a point, hopefully. So what we started to realize, what was really neat about this approach, it allows you to dissect molecules and take them apart now simply on the basis of the carbon being primary or the carbon being secondary or the carbon being tertiary, which is not usually a way you think about how you put molecules together in organic chemistry. And that affords lots of opportunities and lots of different ways to think about how you'd build a molecule. So for example, if you take this molecule, this level of complexity, you can look at this bond, which is, hopefully you can see that bond darkened right there, and you can start to think, well, if we broke that bond apart, right? So we would break it apart, and we can say that we'd make that, hopefully, from 2 radicals. Now, in organic chemistry, we know we typically think we start with one functional group, and we've memorized that it becomes a different functional group or a different bond. But as I told you at the beginning of the talk, we now know with photoredox you can make radicals from almost anything. So as such, you start to realize that potentially you could do this reaction with almost any combination of reaction partners, because it should be agnostic to the starting materials as long as you can make the radical. Okay, if you believe that, you can then start to ask yourself some interesting questions. I told a couple of people this today. We've been working on a reaction in my lab for 17 years with no success, and we've now been able to solve it. And it's the reaction of, can I take any two alcohols in the world, and can I get them to deoxygenate, and then can those radicals selectively react with each other without reacting with themselves? And we can, in fact, now do that. And we can do that with very high efficiency. And the scope of this reaction is really, really exciting. And we just submitted this paper, and it's probably one of the three most exciting papers I think that I can honestly say has come from my group, and something that we're really very excited about. Okay, we'll finish off there. I always like to thank my lab. This is a recent photograph of them taken at Princeton. You know, I think the people in the room probably know this as well. The generation that are coming through labs right now are a very special generation, because they had to do PhDs and postdocs while COVID was ongoing. And what was remarkable about this group of people was they really kept the enthusiasm high, the motivation high. They're all smiling here because I've told them they had to smile, but that's okay. But the point is, they really kept all the institutional knowledge of my group going, and to the point where we kept rolling through COVID, which to the day I finish doing chemistry, I will be unbelievably grateful. I can't thank them enough for doing that. And they're also just an amazing group of individuals to actually work with. And then finally, of course, I have to thank all these agencies, the federal agencies, as well as a whole range of pharmaceutical agencies. And then lastly, all of you for showing up, especially for those of you who are not chemists. If you came along to see a talk from a chemist, I really appreciate you showing up tonight. And if there's any questions about any of this, you know, obviously don't hesitate to ask. And lastly, thank you very much.
Very much, Dave, for this beautiful talk. And the impression is that the now is radical chemistry becoming very, very important. It's the old chemistry that we know for more than 1 century, but now has another view, a very interesting view. With your talk, we realize how important would be in the future radical chemistry. Thanks to the Metallaphotoredox, of course, but I think for the new generations, they can get inspiration with this type of chemistry. Now it's time for questions.
Thank you for this wonderful talk. I wonder if artificial intelligence is affecting the way you are proceeding with this research.
Yeah, I mean, it's not really affecting our ways, because we don't have the intelligence in my group to use artificial intelligence. No, I think it's, you know, one of the things is kind of interesting. So I recently joined the board of this company called Isomorphic Labs, which is in London, who's run by Demis Hebry, who's the famous guy who invented AlphaFold, and he created this company. And so been heavily involved. We sort of talking to them about AI and where everything's going. And it's really fascinating to watch the way I think AI is being deployed right now. And I think it's tricky, because there's parts of it which are very much substantial and real, and there's parts of it which are still in the future, right? And I think the parts which are real right now is, can you optimize any given reaction? So the question of, if I get enough data, like at the beginning of my talk, 10,000 reactions, if I create enough data, can I use that data to improve the reaction? And the answer is unquestionably yes. So you can use AI there for optimization. The problem becomes, can you use AI to invent a new chemical reaction that's unknown? And thus far, no one's been able to do that. And that, at least for now, appears to be a human concept of the invention component. It's not inventing the new conditions. You can invent new conditions to optimize things, but to do something which previously has not been done before is very difficult if you don't have any data that points you in that direction. And that's the problem. So it's pattern recognition or data utility and how it can take you in a different direction. And if you don't have the data in the first place, it's very difficult to make that leap. That doesn't mean to say that won't happen in the future, but right now, I would say for optimization, yes, but for invention, no.
Thank you for your presentation. I have to confess that after 25 years ago, something like that, I read the book by Giese, this book, Black Book. I have never seen something like this in terms of radical, just to bring to a new radical science with, by the way, classical, very classical functional groups, but that is really amazing. But I have a couple of questions related with this. First of all, I don't know if, but there are some examples in which you are forming the primary radical. And I guess that what we explain to students, that radical like to move and to form, to go to the secondary,
yep.
and also to the tertiary radical.
Right.
But you didn't mention about this.
Yep.
I don't know if it's a kinetic control or something like that.
It's an amazing thing. So we were brought up, and I'm the same. That was the way I was taught too, right? Form a primary, it's going to go off, form secondary, form tertiary. But it does that when it's got nothing else to do, because the rate of that is fast, but it's not 10 to the 7th, it's not 10 to the 8th, right? Whereas trapping a metal, like copper, is basically diffusion rate controlled. So even though you're generating primary radicals, before it can do those things we were taught they would do, and they will do, if you don't let them do anything else, they'll go off and they'll trap metals, or in other cases they'll do other kind of chemistry. So the metal interface with the radical component is, I think, really one of the things which allowed radical chemistry to blow up, and in a good way, because it basically is allowing you to sort of tame those radicals, if you want to think about it, because it traps them kinetically faster than it can do almost anything else, and then go off and do other types of reactions. And that was part, I think, was really, it wasn't that it wasn't known, it just wasn't appreciated, where people thought, okay, then we should ignore all of these bad things that we know about radicals because if we throw a metal in, it's just going to clean the whole thing up. And it does. And now we know that, based on the last 10 years, but there's all these other reactions which end up being more facile than those things that we were taught were going to be problematic, including solvent CH abstraction. They will do solvent CH abstraction, but not faster than all the other things we talked about today.
I see. Well, if I can continue, yes. I miss a little bit if this, all this new methodology, because it's impressive, is compatible with asymmetric catalysis or asymmetric induction, or because you didn't mention, it looks like a little bit planar.
Which is kind of funny, right? Because the irony of it, I won a Nobel Prize for asymmetric catalysis, then I don't talk about asymmetric catalysis. You absolutely can do asymmetric catalysis, and there's lots of people who do. Basically, Greg Fu has been a real pioneer in doing so much in that world, and there's tons of other people. At some stage, though, we realized that asymmetric catalysis is great, but ultimately new bond-forming reactions, it becomes even more of a priority, at least for us, because of the impact it's going to have on this very large audience of people who are trying to use it to make medicines. Asymmetric catalysis is amazing when you're scaling up drugs, but in a day-to-day basis, asymmetric catalysis is not going to get used by medicinal chemists. 99% of the time it won't be used. It'll be used by people who are scaling them up, but not people who are in the lab making 10 milligrams of it. They will do what's called separations technology to do that. So ultimately the bond formation becomes the bigger priority. So for us, we focused on that because we knew that it was going to have a larger impact ultimately on the medicinal chemists. However, you're right, once you now get to process, that's where you need all these asymmetric catalytic reactions, and that's why you're seeing people now begin to get deployed or really moving into that world.
I guess that there are other people they like.
Después. Perdón.
Thank you so much. Thank you. Two very quick questions. The first about maybe I did understand well a slide and is related with the chiral information. When you use as a source of radical alcohols. In some slide, it seems that it retains the chiral information.
Right.
Isn't this way? And the second one, so I will finish, is I'd like to have your opinion about the use of electrochemical tools to expand instead of photo.
So two great questions. So the first one is, if you start off with one stereogenic center, and you do photoredox, you're going to lose the stereochemical information. It's gone. So it's going to it could be an enantiopure, it will become racemic. If you've got a 1,2 stereochemistry, or even 1,3, you get diastereo control, which retains the enantiopurity. And then you do the second one, it retains the enantiopurity. So if you've got multiple stereogenic centers, you can induce, right? You can retain. But if you get one, you have to use a metal for cross-coupling that has a ligand on it, which is, you know, what Greg Fu and other people have been doing. So you can absolutely do it. In terms of electrochemistry, I think electrochemistry is fantastic. You know, a lot of people, which I find really bizarre. I always find science is interesting, right? Because at some point it felt like people were trying to move photochem and electrochem into almost tribes. It was like tribalism of people, but they're both based upon electron transfer and the value you can derive from electron transfer. And to my mind, they're both incredibly interesting, but they're different. They're also different, meaning, so for example, when you do photochemistry and you do an oxidation, you do it from a catalyst that can only do an oxidation once. Then that radical has to go and find or do something. If you do EChem and you do an electrode, you can oxidize it, but often it will get then subsequently oxidized again to become a cation. Right? Now you can use catalysts to overcome that, which is also really valuable, but they're different. So I actually think for scale-up, electrochemistry is going to be really, really valuable. And I think for discovery, photochemistry is going to be a little bit more valuable, but they're absolutely both going to be critical. And I think you need both of them. And there are obviously times when those two things will also cross as well. But I do think they're just fantastically interesting opportunities for people to develop new chemistry. And it's often the case you can translate one to the other. I mean I think my favorite one is cross-electrophile coupling, because you can do photo, you can do EChem, you can actually do reducing metals as well, the Dan Weiss approach. So you can do all of those things because it all involves electron transfer. And that's a beautiful case where you can invent in one and translate it to the other ones.
Thank you very much for all of this wonderful, thought-provoking stuff. I was very interested when you said that the 1,2 diols would only react once. Is that specific to the 1,2 diols, or, for example, if you just had a 1,6 hexane diol?
If you do a 1,6 hexane diol, you'll get a statistical mixture. If there's other ones which are not 1,2 or 1,3, we can get them to do it. But it's really because they're doing hydrogen bonding sharing. And when they do that, you can actually put an NHC on one, and it's much more reactive. And the second alcohol is not as reactive once you put the first one on. So it then goes and finds more of the original start material and selectively goes on, which is not something that was obvious whatsoever at the beginning. You sometimes find that with 1,3. We can absolutely do primary versus secondary. It will go on primary, won't go on secondary. The rate differential is so high that you can get them all in the primary, won't touch the secondary. And then, once you're done, run the reaction, let it go a little bit longer, put it all in the secondary. So you absolutely can do those games of do one, then the second one, then the other one.
Wonderful. And the final quick question. I didn't see any vinyl or aryl radicals in at the very end. And how do the sorting? Where do they fit in the sorting?
So we have just. That's a great question. You're asking me something which is very close to the bone now, because it took us. We've taken a long time to get to how we can use radicals to do SH2 from aromatics. And there's an intrinsic problem, which is they're electron deficient. If you think so I'm making an argument these are all nucleophilic. However, if you think about metals that you could use that might solve that problem, we've literally just been able to do that in the past month. But we can now, which I think is really cool, we can now do and we're actually activating CH bonds to become radicals as well, which is really high energy if you think about it. And we can now do those selectively and do SH2. So yeah, there's lots of different things we can do that. The thing there's a lot of different things you can do here. The thing I'm really interested in is, can you take, for example, hexane and dimerize it? Because then you'd be making airplane fuel from hexane, things like that. So there's some really interesting things you can start to play with. You know.
Thank you. Yes, another curiosity, because you had the opportunity, for instance, in Cuban derivatives of generating a diradical at the same time, but you didn't.
No. Well, diradicals are very, very, very high energy, right? That's the problem. I mean, you could do it, you'd be doing it to, you would have to have, for us to do that, you'd have to have some effective point to doing it. other than theoretical. But you could potentially do it is, can you make one and then get it to do the second one? Because cubane radicals are very stable. So in principle, you could make it diradical, but for us, from a synthetic application point of view, it's unlikely we would necessarily want to do that. Unless it was something you're thinking about. I can tell in your eyes there's something you're thinking about, but yeah.
Well, radicals and the radicals are becoming...
Oh, radical combination.
Yeah, because in Cuban you can use a Cuban as a diradical, and then you can play with the alcohol, for instance, or the bromide derivative, just to go to a double reaction. I mean, a twofold reaction. Rather.
Yeah, you can definitely do it sequentially. But you can't do them, we've certainly not been able to do them at the same time, because that diradical species is so high energy.
Yeah.
That's the tricky part.
There are people like diradical species, triplet, singlet, and so on, and to play with this. So with this matter, which is also quite appealing.
Yeah. No, so people, like, you could, but that's getting into sort of more of the sort of physical, organic, theoretical component of, can you actually make them and what would you do with them? Yeah.
Okay.
No, but I think in principle you could, it's just that it's a very high energy species.
So, thank you so much. I enjoy so much your lecture. Thank you.
Hi, so first of all, I want to thank you for this amazing lecture. And before asking, I just wanted to apologize in advance, because I'm basically starting off in this world, so I basically lack all of the knowledge to have a more technical question about this. So I'm going to ask you about something more inspirational, which is basically the main reason I came here for. And I just wanted to know, what was the switching point that made you change from the photocatalysis to the redox one? Because in the end, it's a new technique that you kind of like started out with. There wasn't, like, I'm aware that there was not much knowledge about it previously. So when did you think it was safe enough for you to change fields and explore something like that new before like taking such a big risk?
Yeah, I don't know if, it's not really a case where you sit in your office and think, is it safe enough to change? I think it's more a case of you're doing what you're doing, and then you kind of get involved, you sort of see an idea in a different direction, you go try it, and it works. And you suddenly realize, wow, this could go in all these different directions. And then slowly but surely, more and more of your people in your lab start, and then suddenly you realize this is going to really go in all these different ways. So I wouldn't say, I'd be absolutely disingenuous if I said that was a conscious decision that we were going to go off and do photoredox at that moment. I will say that 4 years into doing photoredox catalysis, you could see that the community wasn't really buying it. It wasn't really that excited about it. And I was sort of faced with a decision, should I keep my lab in that area? Because we were enjoying it, but no one else seemed to like it. And I decided to stay the course. I decided that we should stay with it, because I thought there was going to be really great value there eventually. And maybe 6 months later, Metallaphotoredox came along, and it took off like gangbusters. So unlike organocatalysis, which took off basically in a week, it took like 4 years for more than 4 years for the photoredox stuff to really kick in. But ultimately, I think what you end up doing, you just do what you're excited about, and you go in those directions, and you sort of follow your own sort of magnetic north sort of thing. But it's not really I wouldn't say it's necessarily this really well thought through decision. I think as scientists, we like to retro-engineer it to make it sound like it was well thought through, but it wasn't at all. It was really just, we were in an area and we could see there was a lot of value that kept coming, and we kept pushing forward. I know that's not very inspirational.
Thank you for the talk also. I'm physicist, so I'm a bit out of from this field, a bit. But so I was in contact a bit with the photocatalysis and everything, and that's why I'm here. So my question is related with the power of this light source that you have. So you need to control the power, because at the end, if you put a lot of power, you generate a lot of radicals, and perhaps how much control do you need to have?
That's an absolutely brilliant question. Actually, very few organic chemists or chemists actually have ever asked that question, and it's exactly right, because these reactions are photon limited. The whole rate of these reactions are a function of the power of the light source that we use. And I'll tell you, I shouldn't tell that story because it's on YouTube. I won't tell that story. I came across someone who was actually trying to do these reactions with Christmas tree lights, and I had to explain that was never going to work because they just weren't strong enough. But basically, the more power, the more photocatalysts you can excite, the more the radicals you can generate, the faster, for the most part, the vast majority of these reactions will happen. So when we figured that part out, we were talking to Merck, pharmaceutical company, and we said we need to figure out a way to standardize the way we do this. And so Merck engineers actually built this little photoreactor, which was really cool, made it for a couple of their people. We then took it to an outside vendor. That outside vendor has now sold, I think, more than 10,000 versions of that worldwide. And it's now known as the Merck photoreactor. And every pharmaceutical company, every agrochemical company, all these people use the same reactor because we knew we had to control the photon. Made it to standardize the whole thing with this little device, and it changed everything. But it was all about the photon power, which is at the heart of your question, which is really exactly, it's a great question.
Yeah, thank you.
Hello, Dr. MacMillan. Thank you for the great talk. My question is related to the previous one, but in terms of the wavelength you've used for the lamps, I assume it would be blue light-ish.
Right.
And like, if you did any optimization for the reactions on which exact wavelength, and for the mixture of catalysts, if you had to combine or select the catalyst that would absorb at the same, around the same wavelength, to be able to use them using the same light source.
Yeah, it's also a great question. So number one is we use blue light. A lot of these catalysts actually barely get into the blue region, but they do get in enough, and they have the redox window. The redox window is how oxidizing and reducing they can be, and the ones which have basically the more energy are going to have the biggest redox window. Turns out to be the most useful, which makes sense. So often is the case that they're not well optimized to the light source, but they do work. However, so the second question is, can you actually use different light things to do it? And you can, which is kind of cool, because you can have two different catalysts and they can absorb two different lights. And so you can start to do things which I think, one of the things I think is so cool, and probably the physicists will think is so dumb, but my brother's a physicist and he thinks this is dumb, but basically, can you compartmentalize chemical reactions by time? What do I mean by that? Imagine you have a stroboscope where it goes blue, red, blue, red, blue, red, blue, red, and the photocatalyst can only stay alive for 10 nanoseconds. But the stroboscope is only on for, like, say, 15 nanoseconds. So what you're doing is you're creating photocatalysts that are basically almost continuously excited, but never at the same time of each other. They're compartmentalized in time, so they can't do anything deleterious amongst themselves. So we've been playing a lot with that, as to can you activate different molecules with these photocatalysts and simply using stroboscopic light to drive the whole thing. Which I think is just, even if it never becomes really useful, it's just a cool concept, I think.
Yes, thank you.
Thank you very much for a wonderful talk. Actually, being a physicist, I just tried to understand all the things which you told here, but I just took some part which was interesting for me. Is that you told that you changed that benzene ring to the cubic side of that one, and you told that the carbon bond becomes more stronger at there. So how that carbon bond becomes stronger, and how it can affects on the electronic properties of the material. And you said that it becomes more stable, and in what terms the stability comes, like in terms of moisture, in terms of in what environmental conditions?
So, and I said it, and I probably said it too fast, but it's not the carbon bond that becomes strong, it's the carbon-hydrogen bond. And so when you take a medicine, or you take food, or you ingest anything in your body, you've got cytochrome P450s in your body, which are iron-based, which go in and effectively introduce oxygen into those molecules and make alcohols of all those organic molecules you ingest. And then you do glucuronidation, and it basically your body gets rid of those molecules. It's a way of keeping foreign molecules out of your body. It's metabolism, that's what we call metabolism. So benzene rings, even though they're very strong CH bonds, undergo metabolism by basically an epoxidation rearrangement reaction. Mm-hmm. But cubanes have these CH bonds which are really, really strong, and the reason they're strong, the definition of a bond strength is what would be the energetic penalty to break it into its two components, the hydrogen radical, the carbon radical. And because the carbon radical is so high energy, on a cubane, that makes the bond strength really, really high. And so cytochrome P450s in your body can't readily introduce the alcohols onto cubane, so it can't get rid of them. So if you take a drug that has a benzene in it, your body can get rid of it really easily. You replace it with a cubane, which has a lot of the same properties, but now your body can't get rid of it. You get much longer exposure. Maybe it's 24 hours instead of 5 minutes, and now the medicine can work. The other part is aromatic rings, as you probably know, have these lattice forces that allow them to sit on top of each other. It makes them really strongly, they love to interact with each other, which makes them very poorly soluble. And if things are not soluble, you can't get good penetration into your body, you can't get good penetration into cells. You replace that with these aliphatics. They actually become more soluble, which is sort of counterintuitive to an organic chemist, that these more aliphatic molecules become more water soluble than benzene rings. Somehow it doesn't make sense, but it does actually hold true. And therefore, those two different features of them make them great replacements for benzene rings. It makes them more likely to be successful.
Okay, thank you very much.
Hi, hello. Thank you very much for your presentation and for your time, especially. I was wondering, because you showed us that pharmaceutical technologies such as high-throughput screening can be very useful, and it has been very useful to develop, for example, a way to generalize a reaction. Have you had the opportunity, or was it useful to use any other technologies for your investigations?
Ones which are more available to the any lab, yeah.
Maybe.
Yeah, no, it's a really great question. So for generality processes, you can. I think you can actually do it in a scaled down version to sort of do the same thing. It's obviously going to take a little bit longer, but you can still do it. The one thing though is, I keep coming back to these high throughput systems. I'm still we have one at Princeton. I think there's a couple of universities that have them. They are expensive, so that makes it sound like it's only prestigious or people with money who can get them. But I almost feel like an NMR facility, if we can afford an NMR facility, we should be able to afford a high throughput robotic system to allow us to get to answers faster, where we can focus on what the thing we really wanted to accomplish in the first place. Whether that's understanding a bond formation, getting to mechanistic things, or really just getting an outcome that allows you to get the manuscript to be developed faster.
I was very curious as to whether you've been able to use the radical coupling to make anything that has a significant amount of strain in it.
Yes, absolutely. So we have a paper, it hasn't been accepted yet, but we have a paper submitted to Nature. Anyone can submit a paper to Nature, it's getting it accepted, it's the hard part. But we have a paper submitted to Nature where we've been able to show that we can actually make these really strained bridge bicyclics from radicals. And then I think the point of your question, which took me, I think you figured that out very quickly, it took me years to think of this, is that radicals are so high energy. You think of the energy in a radical, and even if you make a strained molecule from it, it's still lower in energy than the radical.
Exactly.
Right. So you figured that out quickly. It took me a long time to figure that out.
We work with a lot of strained molecules. Small cyclophanes. And the classic example would be, can you make 2,2-paracyclophane?
We haven't tried on that, but we have the paper we're about to publish. I think is going to be, people are going to be really, really interested in it because it's literally these very strained bridge bicyclics that you would see in drug molecules making from very simple start materials through bond disconnections that look like, why in organic chemistry that carbon would never reach around and form that, but then you realize it's a radical. It's so high energy that it's downhill to do that. Even though the strain is high, it's still lower energy than the radical.
This is really, really exciting stuff, so thank you.
Yeah.
More questions?
Thanks so much for this wonderful talk. I have to say that it's very nice to have also in the audience people that are not chemists. I don't know if we have any politician what they could think about doing things with radicals, because we are, as chemists, if they heard that we couple radicals, probably they think we are crazy. Actually, yes.
Yeah.
So my question is a very chemist question regarding the last part of the SH2. So is there any kinetic study to name this bimolecular reaction instead of a unimolecular reaction?
Yeah, so we've actually started to do them. Some other people have done them as well. What you can do is you can actually make the complexes just in a glove box. You can make a metal alkyl species. Then you can actually just generate the radical by any other means. You don't even have to use light. And then study the rate of radical addition into the complex and see the rate at which they're doing them. And the rates are incredibly fast. It's what you would expect them to be. And the reason is the metal to carbon bond strength is usually less than 10 kcals per mole. It's an incredibly weak bond, barely being formed. But that's great because it wants to do the SH2, the metal wants to dissociate, and that's what drives the whole thing over. So the kinetics of it are extraordinarily rapid. So we've been doing them, other people have been doing them, but one of the neatest things is every time you use a different metal, the bond strength changes. It changes the kinetics, but also changes the proclivity of what will actually do the chemistry. That's wonderful as an organic chemist, as you know, because now you can start to think, well, maybe I want to do primary.
Exactly.
So there's all these things that you can start to think about and have selectivity only on the basis of the electronic difference between the two primaries. So I think there's a whole world of things just waiting to be done. It's just getting enough up to speed on what we know on the whole thing.
Okay, fantastic. Thank you so much.
Can I just say, I don't think this is the highest ratio of questions per audience number I've ever seen in my life. This is fantastic. This is better than a group meeting, actually. Yeah, it's good. I love it.
Yes.
Maybe we should finish.
Yes.
This product, are you able to follow all the kinetics of the formation, or you just see the final product?
So in those cases, you can do any step you want. So what you can do is you can see the kinetics of the bond formation to begin with, of the primary on to the metal, or you can do the kinetics of the SH2 subsequently, which will give you the product. But you can nicely slice it all up and do the kinetics of all the individual steps. It's very amenable to that. It's tricky to do it with light for obvious reasons, because the light's continually activating and deactivating. But if you just make a stoichiometric reagent with a stoichiometric reductant that you know forms a radical at a specific rate, and then measure the rate of addition, that figures the whole thing out for you.
Well, I have a curiosity, and I finish. Yes, a small curiosity, please. You always use iridium as organocatalyst, as photoredox catalyst. My question is, why don't you use organic catalyst? It's
a great irony, right? Why we're not using organic catalyst to do the second thing. Basically, we use the iridium because we're cheating. I would say we're cheating, basically. So one of the things we figured out pretty early on is these iridium photocatalysts, which are rare, are too expensive, are never going to get scaled up. But the thing which is great about them is they have these incredibly long lifetimes, and they have really big redox windows. So that means that you can do lots and lots of things with them and discover things far faster than doing the organic one. The good news is, though, once you find the reaction, you develop it, then you can start to find the organic version to do that. And we've done a little bit of that, and you can certainly do it. But for the initial discovery phase, it's so much faster to go with iridium. The one that we just published a paper with Jon Marcaide, it just came out last week, and we showed that you can actually, it was long believed that you could not use first row transition metals to do photoredox catalysis, and we found that you could use cobalt. And we started to, and other people have started to find the same thing, but didn't know why. And it turns out it was because it was in the inverted region, of the inverted Marcus region. So it was actually slow, instead of it going right back to ground state faster than biomolecular chemistry, it could hang out because it's in the inverted Marcus region, so it could live long enough to actually do chemistry. So you can now use first row transition metals and understand why. So there is becoming a whole community of people, I think, that are going off to do that. We think that's fantastic, but I think ultimately we realize we're much more in the reaction invention world than necessarily the catalyst development world. And I think all of those are important, but we really love the reaction invention part.
Okay. So we close the session.
Yeah, we'll close the session. Well, thank you very much. We close the session. Actually, they made so many questions, and that tells something very positive towards the speaker, also towards the public. There must be people who understand chemistry very much, so I'm, in all sense, I'm delighted. So let me hand over to you the diploma of foreign corresponding member
Thank you.
of the Academy.
Wonderful. Fantastic. Amazing. Okay, wonderful. Thank you. Thank you.
Well, that was it.
Thank you. That's awesome. Thank you. Thanks for paying attention as well. I know it's not